Hello, this is Dr. Hassan Abdullah with the course Complexity and Analysis of Algorithms. So, the topic which we are covering is the theory of NP completeness, which is topic 11 as per the course outline. And this is the first lecture on NP completeness basics, so therefore 11A. So, the supplemental material for this course is easymcq.com/goget. And this basically is a learning management system. And it is a personalized learning management system because you can personalize your learning experience through your selection of level of learning, and of course you can route your learning through searching by preserving the order of keywords by pre-order of keywords. How you do that is shown in video 1 and in video 3. You can also personalize the user interface by setting the color, font, shape as per your liking or as per your need, and how you do that is shown in video number 4. And you can have your own personalized exams to check your level of learning with online testing, online grading, and of course analysis of overall results of all the exams you have undertaken. How you do that is shown in video number 5. So these videos about using the tool, and the videos about this course, and the videos about all the courses such as data structures, artificial intelligence, natural language processing, they are available on my YouTube channel and also on the canvas. So just go to YouTube and type my name, Dr. Hassan Abdullah, and these videos will become available to you. So this is the course outline, and you can see the topics which we have here. And this lecture is topic number 11, NP completeness, right? So we move on to the learning management system. So we are at the learning management system, and you can see we have analysis of algorithm, core computer science course, data structures and algorithm, core computer science course, natural language processing, and we also have artificial intelligence, machine learning, and so on. So let's go to the course which we are covering right now, analysis of algorithms, and let's go to the topic of our interest, which is the theory of NP completeness. So these are the questions. The format is questions with detailed answer and bullets so as to convey the concept and understanding. So why study theory of NP completeness? In computer science, we develop solutions to problems. And of course, those problems could be real life problems and difficult problems and not so difficult problems. So the NP completeness allows us to understand the complexity of the problem. Okay. And then it helps us, once we know the status of the problem, the type of the problem, then it helps us in improving the solution, which is the algorithm design. And when we know about the NP completeness, that helps us optimizing the resources, and we are interested in solving the real world applications. So when you go into more detail, okay, so it helps in understanding the inherent difficult computational problems. So there are certain problems which are inherently difficult, which are inherently complex, which are inherently compute intensive. So by the theory of NP completeness, we categorize the problems as NP complete. Okay. And when we do that, then we know that how challenging they are to solve. So then it helps us to identify the challenge. For example, the knapsack problem. So we have a knapsack in which we would like to put in items of different weights and values so as to be within the weight limit of the knapsack. However, this is difficult to do when the input size is large, unless of course P is equal to NP. So what is P and what is NP, that we will cover in this course and this lecture also. So improving the algorithm design. So once we know that this problem is an NP complete problem, so instead of spending lots and lots of hours and time and resources, we move towards the approximation algorithms. We move towards the heuristics. Okay. We move towards the alternative solutions. All of this is covered in this lecture and in this course also. So because why? Because exact solutions are infeasible. For example, for the traveling salesperson problem, which is very popular. So instead of going for the exact shortest path, which starts from a point and reaches that point by covering all the points, like cities where courier service has to drop packages or pick packages, we go towards approximate solutions, providing near optimal results efficiently. The reason being that if, say, for example, we look at 10 cities, because the complexity of traveling salesperson is about n factorial. So if you have 10 points, so that is 3 million and more roots. Okay, and you can imagine when we have 20 points to pick and drop, so that's tremendous, very very large number. So when we understand that this problem is NP complete, then of course, okay, this guides us, right, where we know that the exact solutions are going to be computationally expensive, and there are many problems, okay, which are NP complete, and we will touch upon them very briefly in this lecture. Okay, so optimizing the resources. Once we understand that certain problems are NP complete, then we know that these problems are intractable, right? Okay, so we need to optimize the resources. Okay, because if you go towards a brute force approach, it will consume all the resources all the time and memory. For example, consider the graph coloring problem, which I'll discuss in this lecture also. That is NP complete problem. Right? So that is NP graph coloring is NP complete problem. So instead of unnecessarily exhausting resources, okay, searching for the optimal answer, it is more practical to approach with the greedy algorithms or local search. Okay, of course, they are not going to give the optimal or the best solutions, but they can provide acceptable solutions quickly with less resources. And real world applications, there are quite a few real world applications. For example, in network design, in cryptography, optimization, for example, the traveling salesperson problem, job scheduling problems, which jobs to be given in which order, okay. And of course, they require specialized algorithms. Why? To manage resources efficiently. So once we know that these problems are NP complete, then we apply the right algorithms or the heuristics, okay, or the approximation algorithms for problem solving. Otherwise, what's going to happen? We are going to meet this fate. So there's no point in what this gentleman is doing. So try to conserve your energy and resources. So examples of classical NP complete problems from 5 different domains. So we will cover these domains as you can see here, and these domains are all practical domains, and they are very vital. It's vital that the problems are solved here. So let's start from the satisfiability problem. So what is the problem? There exists an assignment of truth values to variables that makes a Boolean formula true. So we have a Boolean formula with number of variables, right, in a certain form, and the question is that what should be the assignment of truth values such that the overall result is true. And incidentally, this is the first problem which was proven to be NP complete. First problem. And this problem is fundamental to computational theory, and it is used in hardware verification and artificial intelligence and software testing also. So, and of course used in decision making. So this is a cornerstone in logic programming, and I'll show you why it's a cornerstone, and I'll show you in this lecture that why this is the first problem to be proven to be NP complete. What's the significance? Then in operations research, we have the traveling salesperson problem. So the traveling salesman or the person must visit a set of cities exactly once, cities or maybe points within a city, and return to the origin city or the starting point within the city. What is the objective? Minimize the total travel distance, minimize the total travel time, uh, minimize the fuel expenses, and so on. So it has applications in logistics, manufacturing, vehicle routing, and so on. So it plays a critical role in route planning and optimization. And of course, this is computationally infeasible for a large number of cities, right? So that is why we need approximation algorithms, okay, for practical use. So approximation algorithms give a bound that how good the results are going to be with reference to the optimum result. Okay, so that is the beauty of approximation algorithm. So then in bioinformatics sequence alignment by arranging the DNAs, ATCG, or protein sequences, right, to identify the regions of similarity, because the objective is that these sequences or the subsequences are occurring in certain and in different DNA. So how do you align them such that the matching overlap? So this is again an NP complete problem, okay, and even for the variations like multiple sequence alignment problem. And this problem is very critical in bioinformatics for gene identification, for evolutionary analysis, and efficient algorithms are required, right? But since it's an NP complete problem, so we use heuristic methods, right? And instead of finding the exact solutions, we are happy with the solutions which are practical. All right, so then we have the artificial intelligence 8 puzzle problem. So it consists of a grid 3 by 3 with 8 number tiles in one empty space. The goal is to move the tiles to reach a specific goal configuration. This is NP complete problem in terms of the state space search, okay? And it is used in AI research, and it is very computationally challenging, right? And then is a graph coloring problem, classical problem of NP completeness. So we have a graph with vertices and involves assigning colors to the vertices, right? Such that no two adjacent vertices share the same color. Of course, you can assign every vertex a different color. There's nothing smart about it. The objective is to minimizing the number of colors. That's the problem. And it has real world applications in scheduling, resource allocation, and so on. Now you must be wondering that graph coloring is scheduling, traveling salesperson is scheduling, resource allocation, they're very different. Well, they are not different. We will talk about it towards the end of this lecture. Okay, so let me zoom this. So this is what you see at the top is the satisfiability problem. So the satisfiability problem is that given for this, okay, let me make the right selection. So the satisfiability problem is for this expression. Let me change the color. For this expression, what should be the value of these literals such that the result is a 1? So if we take this root, okay, then we have a 1. And if we take this root, then we also have a 1. However, there are other roots. If we take this root, okay, then the result is a 0. And if we take this root, the result is 0. Now the question is that which root should be taken? Okay, so how do we know that when we are here, which root should be taken? How do we know what root should be taken? So it's a very difficult problem. It's very computationally intensive. And this is the sequence alignment. So we can see here that we have different DNA samples here, 5, and and we can say that they get aligned, right? They get aligned based upon the this kind of this is one alignment. They are matching, okay. There here we have a partial matching here, and you can see that we have a better matching here also, okay. And then is the graph coloring problem. So the graph coloring problem is that assigning the colors to the vertices such that the adjacent vertices are different color. So we have the red here, and the adjacent ones are not red. They are not red, as you can see. They are not red. This is also not red. This is also not red. Okay. And the vertices which are adjacent to red, okay, they are not red. So adjacent to red is blue, adjacent to red over here is green. Green here and green here. This is the graph coloring problem, right? So these are NP complete problems, and all right. Okay. So what is the computational complexity class P problems? So we have P type P problems, we have NP problems, we have NP hard problems, and then we have NP complete problems. So class of P problems, and this is the polynomial. P stands for polynomial solvable. So that's a definition. Example of class P problem is like sorting, searching, binary sort, okay, hashing. So significance of class P problem I will discuss. So the class P problems are the which can be solved in polynomial time. By what? By a deterministic Turing machine. So there's a deterministic Turing machine and there is a non-deterministic Turing machine also, which I'll talk about a few questions ahead. So a deterministic machine is like a sequential machine. It works on one solution at a time, and at the end it stops. So polynomial time means that the time taken increases at most as a polynomial function of the size of the input. So as the input increases, obviously more effort would be required, more time would be required. So polynomial means that the time taken is a function of the size of the input. Okay. So if a problem is considered to be of P class, then it is efficiently solvable, and it is solvable in a reasonable amount of time. And the reasonable amount of time is that the number of steps are polynomial. And these problems are set deemed to be tractable problems. Okay. So for example, P sorting, quick sort, merge sort, and searching algorithms, and they are feasible for real world applications. So what is the significance of P is that can be solved efficiently and are practically computable, because the number of steps are polynomial, it's not exponential, and they are considered as a baseline for comparison. Why? Because they are computationally feasible. And we discuss further about NP and NP complete and NP hard, right, with reference to P class of problems. And based upon this, we can distinguish these problems. So this is the importance or significance of class P problems. So what is the computational complexity of class NP problems? So what is that? Let's look at it. So NP is non-deterministic polynomial time. So there's a big difference. So N does not means non-polynomial. Remember, N does not means non-polynomial. Okay. Let me write it for you so that you remember that N does not means non. Okay. This basically means it is non-deterministic. Deterministic. I hope I spelled it correctly. It is non-deterministic. That's what N means. So NP means that the algorithm takes polynomial time on a non-deterministic computer. Okay. So a non-deterministic machine solves them. Okay. And they can be verified. Okay. They can be verified on a deterministic machine. All right. They get verified on a deterministic Turing machine, as opposed to a P class which is solvable in polynomial time. Okay. NP problems can be verified, but the finding the solution may take longer. Class of NP problem, for example, the traveling salesman or salesperson problem that we have discussed, right? So while verifying if a given route satisfy the conditions is easy, you just add them up. Okay. Finding the shortest route is computationally hard. Thus, it belongs to the NP class, right? So if somebody gives me somebody says this is a route, and a non-deterministic machine also gives me a route, so just I add the edge weights of the corresponding graph. That takes polynomial time, right? And for that, I need a deterministic machine. So what is the significance of the class NP? The significance is that NP class contains many real world problems, like for example, the traveling salesperson. Okay. And of course, NP, that these problems are solvable in polynomial time, and those that are not. Okay. And of course, they are solvable in polynomial time on a non-deterministic machine. So the famous P versus NP problem asks whether every problem whose solution can be verified in polynomial time, can it also be solved in polynomial time? Well, it's a major open question. Okay, this is basically what is the paradox of NP completeness. This is the last question in this lecture which I will discuss. So we move on to another class, and that another class is, what is the computational complexity of class NP hard? So NP hard is what? NP hard. NP hard problems are computed that are at least as hard as the hardest NP problem. Okay, and it can be reduced to its polynomial, and every problem NP can be reduced to it in polynomial time. Reduction is not part of this course, but uh, part of advanced algorithm course, which I also teach. So NP-hard problems are not required to be in NP. They do not have to be decision problems or even verifiable in polynomial time. They are generally regarded as intractable. Okay. So Typically, the time complexity is exponentially the worst case, right? Because it turns out to be searching and checking the entire possible solution space. And so, what's the approach is approximation algorithms or heuristics, right? And looking at large number of possibilities. So why they are hard? Because the required solutions grows exponentially as the problem size increases. So getting the exact solution is impossible in reasonable time. So NP hard problems and polynomial time solutions. NP hard problems I believe do not have polynomial time solutions. Okay, and no known algorithms exist that can solve NP hard problems efficiently. Efficiently means in polynomial time. And of course, if somebody discovers and proves an algorithm to solve any NP hard problem, then it would imply P is equal to NP, and which is the biggest challenge of computer science. So the approach is heuristics and approximation algorithms, which is the last topic of this course. So now we move on to the next subtopic.